everybody. Very excited to be here. So I will introduce myself once more. So yeah, I'm Alexandre. I'm working at Linea, and I'm leading the Prover team. So we essentially develop our own proof system for the Linea zkEVM. We also implement it, and we take care of the backend components. And so yeah, I've been working there since the beginning of Linea. Yeah, so in this presentation, I'm going to present essentially where we are on the tech side and where we want to be. So Linea, as currently deployed on mainnet, is a type 2 level compatible zkEVM. So that means that Linea runs EVM bytecode, and there are some deviation with EVM that are sort of minor and that do not appear 99% of the time. Those are the zkEVM, which is not the same thing. We use a customized zkEVM, which is essentially a sparse Merkle tree with some optimizations to make it more efficient to prove and to have less depth. And on top of that, we also don't prove the block hash, we just announce it. Yet it is exactly the same block hash, but it is put in the data availability part. And so what we would like to get to fully align with Ethereum is type 1 level compatibility. That way we'd be able to prove basically any Ethereum version, and it would just work. So our zkEVM is fully covered, fully audited, meaning everything is proven. There is no gap in the zkP. And it's audited, but we believe it's not enough. We believe that it should be formally verified, and on top of that, as part of a deployment, I strongly believe that it should work in multi-prover setting, because like formal verification can brush out the soundness errors, but the correctness and the faithfulness to the Ethereum specification is, I believe, something that will eventually be formally verified, but it's more realistic to have a multi-client as we have today on Ethereum to be fully secure. So on top of that, next, on the performances, so currently the performances that we have are 30 minutes on a large massing, 64 CPUs. We don't have GPU support yet, and it requires 1 terabyte of memory. And there are several reasons for us being so slow. The main is that we haven't had the occasion to focus because we are focusing on having full coverage, so the full completeness. So that's now done. We can now focus on that. And our goal is to be real-time proven as fast as possible. And I will talk a little bit more about our plan to do that in that presentation. So also I mentioned that we are fully bytecode level compatible, but that's not completely true. We do have a censorship axis, which is that we have limits on execution. So the way we structure our zkEVM is as circuits. I will explain more a bit later. It contains several modules, and each module is doing a specific part of the VM, like, don't know, doing the additions, doing the LU, storing the smart contract bytecodes, and so on, so the ROM. And so if we overflow one of these limits, then we can no longer generate a proof. So it's good enough for us to be able to generate proof for 200, 300 transactions. But if we have one edge case transaction that basically overblow one of the limits on its own, then we can't prove it. So that's statistically not a big problem, but like in order to be fully compatible with Ethereum, that's something we need to remove. So I'll talk more about how we are solving this problem. And so one other thing we have is that all the circuits are currently handwritten, so that's amazing for performances. We basically have an order of magnitude better efficiency in the arithmetization. I'll explain more what that means. It's not the prover that is faster, it's the arithmetization that is more efficient. But instead, we'd like to have something where we just write code and then can generate proofs for the program. And we plan to do it without resorting to a zkEVM. So stay tuned for more. And so finally, more stuff on decentralization. Right. So as I mentioned, what's very unique about Linea EVM is that we do not use Linea EVM is that we do not use the zkEVM technique. So the idea of the EVM approach, which is the most common one and has almost become a standard by at this point, is that we do a single circuit that just emulates one VM, and when we want to run and prove something, we just compile that to either the VM that is arithmetized, and we run and we prove that we run the code, which is great because it's arguably simpler. That's why it was. We have already almost production ready or almost production ready zkEVM nowadays, but we waste a potential order of magnitude in terms of performances. So today, to emulate one Ethereum block, it requires 2 billion field elements. So we use a large field, and we are type 2. So that's not a completely fair comparison. And in opposition, if we take a RISC-V arithmetization, it requires between 50 billion and 100 billion field elements. So we can't really have apple-to-apple comparison because we haven't fully implemented the small field support. But we estimate that it will take between 8 to 10 billion field elements to with a small field to replicate our approach. So that's how we came to the conclusion that we can save a full order of magnitude. So as I mentioned, it's very complicated to have your own circuits because you have to write twice the code, you have to write the circuit, and you have to write the witness generator, which is very complicated from an engineering standpoint. It's harder to formally verify because you work directly from the circuit without having a spec of what the circuit is supposed to do. And this complexifies a lot the formal verification effort. It's really complicated when we want to implement something that has a lot of control flow, for instance, the jump test. It also complexifies the effort if we, for the Patricia-Merkle tree, for the block hashing, Bloom filters, all the things that are required by type 1 compatibility that we don't have yet. All of this has a complicated control flow, and we want to work around that. And also, like in theory, I take an analogy. So yeah, writing directly the circuit is more efficient, but in reality, there is a reason why people don't write assembly all from the beginning, and there is also a reason why writing in assembly is not automatically faster. That's because optimizing your assembly takes time, a lot of thinking. And so it means that if you decide to write an entire code base in assembly, it's not going to be optimized because you will just miss a lot of optimization. So the idea is to develop a higher level language that we can actually execute. It's great for testing. And also great if we want to just rewrite something into that language. So what you have is a snippet of what is already available that is computing max. The language will have a lot of high-level facilities, which would be kind of built-in functions. It would also support the precompiles and so on. We still need precompiles, but at least we can write code with it. And we hope to have more maintainability thanks to it. And so the plan with it is that we'll essentially start replacing the low-level modules. Like if we have a module that does a comparison, we'll just rewrite it in that language. Same for the addition. And the goal is that at the end, for each tiny function of the VM, we have a single module that is written in this. And that's great for efficiency because we found that it's actually a lot better to have 100 different modules for small function compared to lots of big modules that are multi-purpose. Right, so that's what the timeline looks like. So we achieved Prover completeness recently. Actually, it was deployed yesterday on mainnet. Pectra is going to come about mid-August, September. And at this point, we'll be fully in sync with the state of Ethereum. That will be a really big milestone for us. And then the focus will split in 3 different directions. So migrating our code base from circuits to the new SM language, migrating to a type 1 zkEVM, and also starting the work for formal verification. Right, so now more onto the prover. So yeah, essentially, I'm going to present a few highlights of what we've been working on. So one reason our prover has a 30-minute latency compared to 12 seconds for most of other projects, despite me claiming that our arithmetization is better, is that we are currently using a large field. I think it explains a lot of that. So we currently, earlier this year, implemented Vortex, which is a polynomial commitment scheme. It's based on lattices, so that one of the big particularity of our proof system. Otherwise, it's very similar to Lirello breakdown, very similar to Stark if you say that there is no fry part. And we implemented it on small fields, and it was a long shot because it's something we wanted to do for a very long time. And now is the moment we can actually work on it and integrate it. And it's just a total game changer in terms of commitment speed. If we count per field element, it's like 300 times faster. And if we count in byte rate, it's 40 times faster than what we had with a large field. So as a result, we have a hash function that is as fast as Blake 2 and ridiculously simple to recurse. And this is the base for our proof system, and the fact that it is very efficient to recurse is also much better in terms of recursion overheads. So that's very exciting news for it, and I'm very excited about it. And yes, we use Poseidon 2 for our Merkle hashing. Because we can't do everything with lattices, because the problem of lattices, they're very fast, but the problem is that in order to be very fast and very secure, we need to have a very large output for the hash. So essentially, each hash is several kilobytes, which is not really acceptable for Merkle tri-hashing. So we use Poseidon 2 for it because it's more efficient. Right, so you can get the link to the benchmark that was done by Yao earlier this week. I'll stay like this for 10 seconds, just so you have a bit of time. Okay. Right, so then now let me present you what I call the Limitless Prover. So Limitless Prover is a fancy name we found for continuation. It works, so one difference with the other approach of doing it is that it's purely at the proof system level. So this way of parallelizing does not know what the memory is. It's purely take a circuit and break it down. So we use a two-step approach, and that's contrast with other techniques. We use accumulators and compare the, accumulator hashes for the looked up values in memory, and check, and then later checking, and because we can then, and we do it in two steps. And so when we do it with an accumulator hashes, we can do it in one step. Yet what was very important for us was to have a fully asynchronous workflow. Because when we go in production, having a system where we just distribute the prover and have a synchronization barrier, and then if one of the prover crashes, we have to restart all over again, was like a no-go. So we opted for it, and we design around this problem. And so we do one step where we don't need the shared randomness, and one step where the shared randomness has been generated, and we can work out the rest. And the conglomeration part is where we aggregate everything. So GAL stands for global local. So it means that we prove all the arithmetic constraints, and local constraints are arithmetic constraints, but just as a single point, and global is for entire columns. And LPP means lookup, projection, and permutation. So that's all the constraints that requires shared randomness in order to be compiled. So there are several ways of doing it. And in every situation, we need some randomness. So that's great because it will allow us to reduce the memory requirement from 1 terabyte to 64 gigabyte. Kind of a refresher, honestly. It will save a lot on the cost because running on smaller memory machines will just kill, will basically allow us to just run on smaller machine, and so less expensive computation. It will help us lower the latency because instead of having a big monolithic workload, we can chop it down into smaller machines and it will just run. And there is a pay-for-what-use effect that is really interesting because, as I mentioned, we have a big monolithic circuit, so it's not completely used, and too bad, you still pay for the entirety of it. And so with it, we will be able to chop down the circuit and only reuse the part that we need. So if we don't have pairings, we don't pay for the pairing parts, for instance. And basically, it's a 70% saving for us, so really welcome. Right, and so finally, I talk a little bit about the work of the amazing NORC team and what they did. So they worked a lot in optimizing the precompile. So the way we handle the precompile is they write a Planck arithmetization of it, and we embed it in the proof system as our zkEVM proof system that's called with framework that's called Wizard can basically subsum the Planck arithmetization, as you can do fixed permutation, you can do global constraints, and all of this combined gives you a Planck arithmetization. And so they really optimized crazily those precompiles. So they published, so yeah, Youssef, Thomas, and yeah, others from other projects developed a new technique called fake GLV, which is a technique to improve by 30% to 50% the cost of doing any simul in a circuit. They also deliver two optimization in non-native arithmetic and extension field arithmetic in circuits. And this is using quotient verification batching, which was a technique that was already known, and it's not pioneered, but basically it allows us to have less than 100K constraints for zkEVM verification in a vanilla Planck. We do other optimizations such as GKR in non-native arithmetic. So this one has not been shipped, but that's a 10x improvement just for this precompile. We are also considering doing it for pairings because the technique can just be adapted for every other elliptic curve precompile. And it's working amazingly well. The idea is that the GKR circuit is in the non-native field, but the verifier is on the native one. And the only expensive thing in GKR for the verifier are hashes. So native or non-native does not matter. We can just use a native hash function. And so in what's come next, we have techniques to efficiently check that a final X does not return one. So we had one to prove that it does return one, but not for the contrary case. So stay tuned. And we are also working on a batch subgroup membership technique. Yep. And so to conclude on decentralization, so currently Linea is at stage 0 of decentralization. And that's because we missed two things to be stage 1. So we need a first censorship resistance mechanism. So the one we choose is first transaction because we think it's simpler. There will be later stage. We're also thinking about moving to base rollups. Because we think it's the best solution, but that's not the only one that we are looking at. We also think that having our own consensus algorithm could be a good idea for decentralization. Not everything is decided yet, but presumably we are going to go with base rollup. And we also need to increase the exit delay from 2 days to 7 days. And to go to stage 2, we need to have the decentralized governance and a 30-day exit windows for non-security related upgrades. Right, that's it. I believe I'm just on time, so there shouldn't be too much time for questions. So yeah, feel free to just harass me after.